So today we will continue with the matter that we started yesterday, which is the types of reactions in metabolism and which we'll see in the various metabolic pathways, and the related enzymes and cofactors which are connected with these kind of reactions. So as I said yesterday, it is a preparation for the specific metabolic pathways, because then when you see the type of reaction, hopefully you will have something to refer to and say, yeah, obviously this reaction we need NADH or FAD or something like that in order for the reaction to go forward. Now, just a little feedback, because you don't really write any evaluations or nothing like that, unlike the Czech students. I just want to hear a little bit of feedback, whether it's yesterday's lecture, whether it was something you could follow, or whether it was something that was way out there and it made no sense to you. So just maybe raise your hand if it was easy to follow and you got something out of it. Okay, not a lot of people are raising their hands, okay. Okay, raise your hand if you believe it should be done differently, that it wasn't really useful for you, yesterday's lecture. Okay. Okay. So, some people, yeah? Not really. I really don't think so. Okay, because we will go actually quite a bit deeper in the metabolic pathways. So this is a general introduction. I mean, there may be a few things that are more, if you find them interesting, but the majority of stuff that we covered is not really going too deep at all. Okay, we'll be delving deeper in later lectures. Okay, so I don't have that feeling that it will go too far. Quite the contrary, I would say. It's kind of a gentle introduction. Yep.
Is there a way to close that?
Yeah, I can do that. It just felt like it's fine. It's not a problem. But I don't think it feels like I can see that, but it just feels like 1/3 of the okay. There we go. That's better. Okay. I think some of the lights are not working for some reason. Yeah. Oh, they come. All right. Good, okay, so it's not too far out, that's good. So I'll continue in the same way. Again, feel free or, do ask questions because it's quite important. And again, I understand that you have slightly different backgrounds in chemistry. So this is also an opportunity for everybody to get on the same page, hopefully. So continuing with reactions, we will now deal with a couple of reactions, so a forward and a reverse reaction, which deals with the addition and the removal of a carboxy group. So we'll be talking about carboxylation and decarboxylation. Carboxylation, decarboxylation. So that means carboxylation is usually an addition. So we have some compound, like so, for example, okay? We add carbon dioxide. Usually, carbon dioxide in carboxylation is added as a bicarbonate ion, okay? So remember when we spoke about carbonic anhydrase, we said that if you dissolve carbon dioxide in water, it would spontaneously turn to bicarbonate and protons, okay? And we have an enzyme to speed this reaction up. So the real reactant in carboxylation is bicarbonate. I won't go into the mechanics of the reaction. Again, if you're interested, you can look it up. It's interesting, and maybe I don't think we'll actually look at it. Anyway, so there's bicarbonate that goes in and forms a carboxy group, like so. Okay, so it forms a carboxylic acid directly from carbon dioxide. Now this is, in practice, this reaction is what we would call a fixation of inorganic carbon dioxide. So you know that plants, when they make, through photosynthesis, when they make their sugars, they take carbon dioxide from the air, and turn it into sugars or amino acids or whatever. Okay, and this is called fixation of inorganic carbon dioxide. Does it make sense? Okay. In humans, in animals, this is not a usual reaction. That's not how we produce most of the components in our body. But here is one reaction where we actually do that. We take carbon dioxide, well, from the air or from some other metabolic pathway, and we add it we join it with some organic substance. Okay, so this is just an interesting reaction which brings us a little bit closer to plants. Not really, but you know what I mean. Okay. In order for this reaction to work, in the majority of cases, we need to do some work. We need to add some chemical potential. We need to add ATP. And ATP is hydrolyzed to ADP and sometimes to AMP. So there's a hydrolysis of ATP in order for this reaction to proceed. That means that carboxylation on its own would not be a spontaneous process. Okay, so it's not thermodynamically spontaneous. We have to help it in certain ways for it to proceed. Yesterday when I had a lecture for Czech students, one of them said, yeah, but you say that the majority of carboxylations need ATP, but actually the most abundant enzyme on Earth is a carboxylase and does not need any ATP. And that is true because the plant enzyme, which is called ribulose 1,5-bisphosphate carboxylase, don't worry about it, okay, it's the plant enzyme in photosynthesis, which is a carboxylase, but it does not require ATP because it achieves the spontaneity of the process by doing something else, because it then oxidizes the product and that kind of pulls the reaction through. Okay, so it doesn't use ATP, but it still use something to power the carboxylation, because carboxylation on its own would not be thermodynamically feasible. So we'll see a few carboxylations in the metabolic pathways that we'll look at, and almost all, if not all, the carboxylases that we'll see in metabolism contain one specific cofactor, one specific coenzyme, and that is called biotin. So biotin is a cofactor of carboxylases. Again, something that you should connect in your head, okay? And when there's a carboxylase, just think biotin. It's not always true, but it's almost always true, okay? What is biotin? Has anyone heard of biotin? Okay, it's a vitamin. Yeah, it's a vitamin. Yeah, I guess. Yeah, B7. So either it's put into the B vitamins group, or sometimes it's called vitamin H from, in historical reasons, sometimes it was called vitamin H. Either way is fine. If you call it biotin, that's what I like the best. Okay, it's biotin, part of B vitamins or vitamin H. Very interesting chemical structure. Again, those of you who like chemistry, have a look at what biotin looks like and also what it does in this specific reaction. The enzymes that catalyze carboxylation are generally called carboxylases. Okay, so something carboxylase. And they fit into the class of ligases, which, if I'm not mistaken, is class 3. Is it 6? There we go. Class 6, ligases. Okay, because they form a bond between two carbons. That means that there are ligases. Okay? Do you have a question? The what? That carboxylases, the enzymes that catalyze carboxylation, belong into the group EC6, ligases. Okay, so ligases is the class. Again, yesterday I already said, have a look in your workbooks. Okay, now at this point you should be really going through your workbook, and there's a nice table of all the classes and the subtypes that you find there. Okay, so at this point you should be looking into that and learning that.
The workbook is the workbook of design chemistry?
Yep, of course. For course 2, there's a workbook. It's not just biochemistry, it's course 2 workbook, so use it. Okay, there's a lot of important and potentially even interesting information there. Right. Questions? Yep.
What is that? What are you showing?
You want me to go through the whole thing again?
What
It's called carboxylation. I'm not sure where the question is heading. This reaction that I show here is called carboxylation. Yeah? Requires ATP, generally requires biotin as a cofactor. The reverse reaction is called decarboxylation, as you would probably expect. It is the removal of carbon dioxide from a compound. So usually, well, always, we have some carboxylic acid, which becomes decarboxylated carbon dioxide turns into bicarbonate very quickly, okay, or there is an equilibrium between the two, and the compound becomes decarboxylated, okay. The decarboxylation reaction generally is spontaneous. It doesn't require any work done, it doesn't require any ATP. Okay, so it's spontaneously, lots of compounds spontaneously, thermodynamically spontaneously decarboxylate. Okay, but we do need, for this reaction, obviously we do need catalysts, we do need enzymes. These enzymes are usually, but not always, and I will tell you some exceptions, but important exceptions to the rule, they would be normally called decarboxylases. Okay, however, they're not always. Okay, I'll show you in a second some enzymes that are not called decarboxylases, but they are decarboxylases really. Now, decarboxylases do tend to have a few different coenzymes in order to be able to catalyze this reaction, and I will show you two types of coenzymes that are used in decarboxylases. Okay, there may be other ones, but I will show you the ones that we will see a few times in metabolism. So one type of reaction which requires a specific coenzyme is the decarboxylation of amino acids.
Why did we here not remove bicarbonate ion?
Yeah, so in the reaction, usually what is removed is really carbon dioxide, which is then turned into bicarbonate. Okay, so the reaction mechanism, here it usually requires bicarbonate, here it forms carbon dioxide, which is then turned to bicarbonate. But don't worry too much about these differences. So if you put here carbon dioxide and if you put here bicarbonate, that's fine. Okay, it doesn't really make any difference. From the point of view of the reaction mechanism, it does make a difference, but we don't really deal with that. So don't worry about it. Okay, either's fine. You can just put carbon dioxide everywhere. That's not a problem. All right, so decarboxylation of amino acids is something that we'll see primarily in the third course when we speak about signaling molecules and metabolism of signaling molecules, okay? But it's something that occurs repeatedly, and if we decarboxylate an amino acid, we get a primary amine. Okay, so we remove carbon dioxide and we get an amine. Okay, we will see that in the synthesis of adrenaline, synthesis of dopamine, synthesis of serotonin. All these neurotransmitters in the central nervous system contain this type of reaction. Now, for the decarboxylation of amino acids, and actually the majority of, well, lots of reactions with amino acids, we need a specific coenzyme which is called pyridoxal phosphate. Pyridoxal phosphate. How does pyridoxal phosphate, who's heard of pyridoxal phosphate? No one's heard of pyridoxal phosphate? Pyridoxal phosphate. Huh? Correct. It is derived from vitamin B6. Okay, so it's which is actually a mixture of several different compounds. Okay. Yeah, pyridoxine, pyridoxal, pyridoxamine, pyridoxal. There are a few different forms of vitamin B6, but they are all in our body. They are all converted to the coenzyme called pyridoxal phosphate. Okay, so that's the active form of vitamin B6.
This is the coenzyme?
That's the coenzyme, okay? It's actually a prosthetic group, okay? So it's actually part of the enzyme, it's covalently linked to the enzyme, it's not moving around, it's hidden inside the active site and it just stays there unless something really, really bad happens, okay? So it's a prosthetic group in most enzymes, probably in all enzymes. So what does this pyridoxal phosphate do? Let me just erase one of the bits there. Pyridoxal phosphate, as the name suggests, hopefully, contains an aldehyde group. So it looks like this. Okay, some stuff hanging off it, we don't really care about that, but we care about the aldehyde group, that's important. And it is the aldehyde group that allows pyridoxal phosphate to be a coenzyme for a lot of reactions with amino acids, and the reason for that is that this aldehyde really likes to react with the amino group. Okay, so it binds the amino or reacts with the amino group, water is removed, and a structure which looks something like this. Let me just redraw the cycle. Okay, a structure looking like this, whatever, okay, is formed. So we take the aldehyde, we react it with the amino group, and this thing with the double bond is formed, which is called generally a Schiff base. It's a Schiff base. Just a second. Those of you who've done a little bit more of organic nomenclature, what would be the name of this thing? Nitrogen, double bond, carbon, carbon, nitrogen, double bond, carbon. It's called imine. Yeah. Okay. So Schiff base is really an imine with some aromatic ring attached to it. Okay. You had a question?
Yeah, what part is the shift base?
What?
What part is the shift base?
It's a reaction between this aldehyde and this amino group that forms a Schiff base. So it's an imine with some aromatic ring attached to it. It's called a Schiff base. So the amino acid goes into the active site. There is this aldehyde group waiting, and it reacts with the amino group. Water is removed, and this is what you get. Yeah? Okay, so this oxygen goes away, these two hydrogens from the amine go away, and you have this structure. Now, in the case of amino acid decarboxylases, the formation of this Schiff base, plus some additional things in the enzyme, which I'm not going to go into, destabilize. They move electrons away from this bond, they destabilize it, which then allows carbon dioxide to move away. Okay? And the rest of the amino acid remains attached to the coenzyme covalently. This is what?
In what case?
In the case of amino acid decarboxylases. So I'm just showing you now the reaction mechanism of an amino acid decarboxylase.
It releases carbon dioxide.
Yep. So this thing forms in the active site. There are some other things removing electrons from this thing, which means that this bond becomes really weak and the carbon dioxide just moves away from it. Okay? And we are left with the bit of the amino acid attached to the coenzyme. Okay? Now in the next step, a molecule of water comes in. Another molecule of water comes in and hydrolyzes this Schiff base, which gives rise to an amine, and the Schiff base, well, the pyridoxal phosphate is regenerated. Make sense? Relatively simple mechanism. Okay, remove water to form Schiff base. That destabilizes the bond to the carboxy group, which is released. And then another water molecule comes in, dissolves the Schiff base, and we're left with an amine and a regenerated pyridoxal phosphate.
Not an amine, a part of it. Oh, the amino acid part is an amine.
Well, the final product is an amine, yeah.
Which is only a part of the
Yeah, of course, yeah. It's the amino acid without the carboxy group, is an amine. Yeah, so one water molecule is released when the Schiff base is formed, and then another water molecule comes in and then dissolves the Schiff base, but it's already without the carbon dioxide within the carboxyl group. Okay? So that's one specific type of decarboxylation which uses pyridoxal phosphate. Pyridoxal phosphate, again, connected in your heads with amino acid metabolism. Okay? If something happens to an amino acid, if you don't know, just say pyridoxal phosphate, okay? It's quite likely it's going to be true, okay? Those two things are very often tied together. So that was one type of a very, very simple decarboxylation, okay? Now I'm going to show you an example that we'll see actually next week already in specific pathways, in specific metabolic pathways, which is also a decarboxylation, but the mechanism is a little bit more involved, a little bit more complicated. It's not a decarboxylation of amino acids, it's actually a decarboxylation of alpha-oxo acids. So the same way as we have here an amino group on the alpha carbon, that's the alpha carbon, right? Because it's an alpha amino acid. Okay? So we can also have an alpha-oxo acid. Does anyone know any alpha-oxo acid? Yeah, pyruvate is an alpha-oxo acid, right? And we'll see other ones next week, like ketoglutarate, okay? So the decarboxylation of alpha-oxo acids is actually chemically really difficult, okay? They don't really want to decarboxylate for some reasons, okay? On the other hand, and I will show you the decarboxylation of alpha-oxo acids, but if we have beta-oxo acids, these ones decarboxylate really happily. They will spontaneously, if you just let them alone, they will decarboxylate. Something that we'll also see in metabolism, okay? But that's the easy bit. Decarboxylating alpha-oxo acids is a bit more difficult. So for that, we need both a very special coenzyme and a slightly more complicated mechanism. The coenzyme which starts the decarboxylation of alpha-oxo acids is called thiamine pyrophosphate. Thiamine pyrophosphate, or thiamine diphosphate is actually the correct name. That's the coenzyme, okay? The enzyme, well, I'll tell you what the enzyme is called, okay? It's actually not called decarboxylase, unfortunately. So thiamine pyrophosphate or thiamine diphosphate, okay, is the coenzyme, which is the active form of a vitamin B1, okay? So it's derived from B1 vitamin, and it's the active form that we find in several different enzymes. Now, what is so special about thiamine pyrophosphate? It's one of my favorite coenzymes. Yeah, I do have favorite coenzymes. Yeah. Why is it so much fun? Sorry, like so, like so. Sorry? Is it? Not really. But let me just give it the correct, yep. It's here, yep, that's correct. Here, and there are some things hanging off it. Don't worry about these other things. This is the This is the interesting part of the molecule. Okay? Thiamine pyrophosphate is a bit more complicated, but this is the interesting bit. This is the diphosphate, yeah, hanging off it, okay? But again, those are the uninteresting bits, okay? This is the interesting bit. Does anyone know what the name of the heterocycle is? Yeah? No. Because there's a nitrogen there as well. It's called thiazole. Thiazole, okay? And it's a 5-membered ring, thiazole. Don't worry if you've never heard it, yeah, but correct name for the ring is thiazole. And it's a very unusual thing to see in biochemistry especially, because this carbon atom has very interesting neighbors. First, it has a positively charged nitrogen on one side, and on the other side, it has sulfur. Sulfur is a very electronegative element, so it will be pulling electrons towards itself. It likes to bring electrons, okay? And the positively charged nitrogen, of course, will pull electrons to itself as well. Okay? So that means that this carbon is really starved of electrons, okay? It doesn't have a lot of electrons, which destabilizes the bond with hydrogen. Okay, so imagine that the electrons that form the bond with hydrogen are pulled away by these two electronegative elements, and this bond becomes destabilized. And what happens in the enzyme is that the hydrogen is released as a proton, and what we are left with is a negatively charged carbon. Make sense? Maybe? Not really? Huh?
And then it's not stable.
Well, it's very reactive indeed, and that's what we need. But I will just briefly explain it again, okay? So in the thiazole ring of thiamine pyrophosphate, we have a carbon atom which has two very electronegative neighbors, okay? So elements or atoms that really want to pull electrons away from it, which is the positively charged nitrogen and this sulfur. So they are pulling electrons, and as they are pulling electrons away from the carbon, that also means they are pulling electrons away from this bond between this carbon and this hydrogen. That destabilizes the bond, and the hydrogen goes away as a proton. It's released as a proton. So you could say that this whole thing becomes very acidic, okay? That this carbon becomes acidic, it releases proton, but when it releases proton, of course, it has to be negatively charged, right? Because now there are more electrons there. Yeah? This negatively charged carbon in general organic chemistry is called carbanion. And it is an extremely reactive species. Okay, so it does exist even in like organic chemistry and organic synthesis, but it's not an easy thing to make, okay? Because it's unstable, you need lots of things for it to happen. But it does happen in our enzymes. Yeah, so if you see a compound with a negatively charged carbon, it's called a carbanion. Well, basically all of the molecule, or I mean, the negative charge is centered on the carbon, on this one, but the whole thing behaves as a carbanion, okay? As we said, it's extremely reactive, and in the case of an alpha-oxo acid, it will react, so the alpha-oxo acid comes into the active site of the enzyme, okay? And there, this carbonyl atom, this carbonyl carbon, is slightly positively charged, again, because the oxygen is pulling the electrons away from it. So it has a slight positive charge, okay? Not a real positive charge, but a tiny partial positive charge, okay? It's usually denoted as delta plus, delta meaning partial, okay? In the active site of the enzyme, this delta plus carbon reacts with this negatively charged carbon, and they form a bond like so. And this formation of a bond, because of course you can see that it would form a 5-valent, pentavalent carbon, right? It's the 5th bond already coming to the carbon. Can you see that? Yeah, so one of the bonds has to go away, okay? And it's this bond that goes away. Well, there's one bond, second, third, fourth, and this would be a 5th one.
And then the CO minus
Goes away. Okay? So that's a decarboxylation that happens with alpha oxo acids, and one typical type of this alpha oxo acid, which is decarboxylated like this, is pyruvate. Okay, so decarboxylation of pyruvate starts with this reaction. However, that's not the end of it. The enzyme that decarboxylates pyruvate, which, by the way, is called pyruvate dehydrogenase, and we'll see in a second why it's called pyruvate dehydrogenase. Potentially confusing, okay? Decarboxylates it, but it's called dehydrogenase, but we'll see in a second what happens. Well, the enzyme becomes modified by this residue. So we're going to have something like this hanging off the enzyme, or the coenzyme rather, the thiamine pyrophosphate. And in a few more steps, like 4 other steps or something like that, this thing is further oxidized to a carboxylic acid, to another carboxylic acid. Okay, I'm trying to give it to you in small parcels, okay, because the whole enzyme of pyruvate dehydrogenase, which catalyzes this reaction for pyruvate, contains 5 different coenzymes, okay, and thiamine pyrophosphate is the first one. So this thing, well, in the case of pyruvate, if we take the case of pyruvate, there's not going to be R. It's going to be methyl group, right, for pyruvate. So this thing hanging off the thiamine molecule will then become oxidized. So it's actually moved between different coenzymes like dihydrolipoic acid and coenzyme A and FAD and NADH, okay, several different coenzymes. It becomes oxidized and becomes acetyl, it becomes acetic acid in the end. We'll see that when we talk about the Krebs cycle, because this precedes the Krebs cycle, this reaction. But this is just a little preview. The end product of this reaction will be acetyl-CoA, acetyl coenzyme A. But that's something that we'll see later on. Here, I just wanted to show you the function of thiamine pyrophosphate in this type of decarboxylase. And I said that the enzyme that catalyzes this is not called a decarboxylase, it's actually called dehydrogenase. And the reason is that this type of decarboxylation is actually called oxidative decarboxylation, because it combines decarboxylation, which is the step that we saw, and then in the next step there is an oxidation, which I'm not going to show you now, okay? But these two things together are called oxidative decarboxylation, and that's the reason why the enzyme is called a dehydrogenase. It should be called perhaps decarboxylase dehydrogenase or something like that, or decarboxylase oxidase or something like that.
Both of the reactions are the same enzyme?
Uh,
In the
yes.
There's like one product.
And this thing is then moved on to a different coenzyme. There it is oxidized, then it's moved to a different coenzyme.
But
Yes.
It's within the same enzyme.
It's within the same enzyme. Yeah. It has actually, these enzymes have 3 subunits, but that doesn't really matter. It's within the same enzyme.
The enzyme? Because
Well, if we take this alpha oxo acid to be pyruvate, then the enzyme is called pyruvate dehydrogenase. But we'll see pyruvate dehydrogenase next week, okay, when we talk about the Krebs cycle.
here. Where did the double bond go?
Yeah, so these electrons move to here, and there's a proton that comes here, okay? Then we have the one bond here, okay? So that gives you the OH here, okay? You can look up the actual step-by-step reaction mechanism if you're interested. I'm showing you a slightly simplified version of what goes on there.
What's the name of the title of the reaction?
The what?
Can you look it up?
The what?
The title of the whole reaction.
I'm not sure what you mean by that. It's a decarboxylation. It's an alpha oxoacid decarboxylation, generally speaking. And as an example, we took the pyruvate dehydrogenase reaction as an example of that. Okay, so you can find it under pyruvate dehydrogenase or alpha oxoacid decarboxylation or oxidative decarboxylation, I guess that's the best name for it. So just one second. So what I wanted to show by these two specific examples, but there are also different kinds of decarboxylations. So those are not the only two kinds of decarboxylations. But I just wanted to show you that unlike carboxylation, which is usually the same reaction, okay? We have biotin, we have ATP, we add CO2, that's it, okay? For decarboxylation, there are many different subtypes of decarboxylations. Decarboxylation of an amino acid, oxidative decarboxylation of alpha oxoacids, etc., etc. There are different types of carboxylations. They need different coenzymes. They require different conditions. They require different enzymes. They give different products, okay? So there are lots of different types of decarboxylations. Yes?
When we further oxidize this product, we oxidize the alkyl group or the OH as well?
The OH.
So this part is untouched, so it will be COOH here.
This is untouched.
Yeah.
This will become oxidized to a carboxyl in the end. But we'll cover that, okay, in next week, so don't worry.
What happened to the hydrogen?
To which hydrogen? The proton? Don't worry about protons. They come and go. There are lots of protons everywhere.
Okay, so I understood until this step. Is it the final step?
No, but wait. This proton left the coenzyme in the beginning. That was the very first step. It just left, okay? And it formed the carbon ion. So it has nothing to do with this, okay? That's like in the next step, okay? Yeah.
So you said that there will be a different coenzymes until the end product.
Yes.
And the oxidation will be on the group connected
Yeah.
to the
But again, we will go through this reaction next week, okay? So don't worry about the additional steps that occur in the enzyme, okay? Good. Any questions about this mechanism? Yep.
Where is the OH?
So we started with the keto group here, okay? Now this group moved here and a proton was added to it, and that's the OH group. In a simplified way, okay? Good. Maybe let's take a 5-minute break. And we'll continue with the rest of the reactions. So, decarboxylases, so we said that carboxylases are ligases, okay? Decarboxylases are generally lyases, okay? So they are the enzymes that break carbon-carbon bonds. Makes sense, okay? Now, of course, in the case of oxidative decarboxylation, there's also a redox component to it. So they will be, at the same time, they are dehydrogenases. They're also oxidoreductases, just so you know. It's a mix. There are two reactions going on at the same time. Good. Let's move to the next reaction, again, which we'll see many, many, many times in metabolism, and it's very useful, metabolically speaking. And this reaction is called transamination. So transamination Transamination is a reaction between an amino acid and an oxo acid. And the two molecules, swap the amino group. So from the amino acid, we get an oxo acid, and from the oxo acid, we get an amino acid. That's transamination. So it's really moving of the amino group from one molecule to another molecule. So we can have an alpha amino acid looking like this. I'll use a different color for the oxo acid. Okay? And transamination or transaminase enzyme takes this amino group and moves it here. So we end up with an oxo acid and an amino acid. Like that. Okay? It's literally taking this amino group and moving it here. All the transaminases that we'll see contain as their cofactor pyridoxal phosphate. Again, if you hear something about amino acids, okay, always think pyridoxal phosphate. It's not always there, but oftentimes you'll be right. Okay? So the coenzyme here is pyridoxal phosphate. We have it here. And the reaction mechanism is actually quite similar to what we saw with the decarboxylases of amino acids. So first the pyridoxal phosphate comes, or the amino acid goes into the enzyme. Yeah, whatever. The amino acid comes into the enzyme and forms a Schiff base with this aldehyde and pyridoxal phosphate. Okay? PLP, pyridoxal phosphate. Yeah, it forms the Schiff base. We saw that before. So that's the Schiff base formed from the amino acid. That's pyridoxal phosphate, it's the abbreviation for pyridoxal phosphate. So we form a Schiff base by removing water. Yeah? It's a condensation reaction. We remove water for that. Yeah? And then we add another molecule of water, but this time we hydrolyze the Schiff base in such a way that it hydrolyzes this bond rather than this bond. And we get an oxo acid out of it. Can you see it? Or do you want me to draw it in steps? Okay. So we have water that comes in. Yeah? And it's not really addition, but it kind of moves to this bond, and the OH forms an oxo group here, and the hydrogens basically form an amine here.
From where is the other hydrogen?
From the water.
Yeah, no, like the NH2, one is we got it from the water. Where is the other H from?
Well, there was another H here, okay, as well.
Oh,
But again, don't worry too much about where all the atoms go, okay? That's not that important. Just, it's more important to get a general idea of what happens here. So in the first step, the amino acid gives away its amino group to the enzyme, and the enzyme becomes changed, right? There's a covalent change because we started with an aldehyde here, and now we have an amine there. Yeah?
you form an oxo group here?
Yes. In the next step, and this keto, this oxo acid, goes away from the active site. And a different oxo acid comes in, binds to this amine, forms a shift base. Another water molecule comes in, and then hydrolyzes this nitrogen, and a newly formed amino acid goes away. No? Really? Okay. Well, let's do it in an even more simplified way. So, this is the active site of the enzyme, okay? I'll do it super simply. An amino acid goes in. An amino acid comes in, okay? And leaves the NH2 in the enzyme and goes away as an oxo acid because water comes in and makes it into an oxo acid. Sorry, into an oxo acid. And the NH2 stays in the enzyme, okay? And then an oxo acid comes in, a different one, and takes this amino group and becomes an amino acid. So it's a two-step process, okay? First acid goes in, leaves the nitrogen in there, leaves as an oxo acid. A different oxo acid comes in, takes the nitrogen, and leaves as nitrogen, the amino group, and leaves as an amino acid. This is quite interesting because you can see that halfway through the process, the enzyme is changed. It doesn't work as a catalyst, okay? It's covalently changed, okay? Same thing that we saw before with the thiamine pyrophosphate, okay? For a bit, the enzyme is changed, and we have to do other things, other steps in order to regenerate the enzyme so that it can work as a catalyst again. So halfway through, the enzyme would not work as a catalyst at all. Okay, lots of you look really uncomfortable with this, and I'm not sure what the problem is. So ask questions, because this is a reaction that we'll see many, many, many times in different contexts. Yep? Yeah, that's a good question. So how come that, first we hydrolyze this bond, then we hydrolyze a different bond? Well, that's really given by the configuration of the enzyme and by the configuration of amino acids around, okay? So I'm leaving out a large part of the enzyme mechanism because it would be really complicated, okay? But the amino acids around are capable of bringing a hydroxyl, a proton where it's needed throughout the process, okay? So that's what determines which bond will be released, which will... No, it's one after another, but as it happens, the enzyme brings, or the other amino group, the other side chains of amino acids will bring all the different components that are needed in the right time, in the right direction, okay? But this is massively simplified compared to what actually goes on in the enzyme. But that's what determines what happens, okay? Yes?
The product that would leave first of all, what is the name of the enzyme?
Usually they are called transaminases or aminotransferases. Both names, you will come across both names, but transaminases is the correct term.
The part that undergoes this reaction is the enzyme or is the coenzyme? The part where the removal of the
So the coenzyme is covalently bound to the enzyme, but these things happen on the coenzyme, on the pyridoxal phosphate. But with help of other parts of the enzyme, of course. It wouldn't work just with the coenzyme.
Why do we need it if it creates the same molecule?
Excellent question. Okay, I was just getting that. Perfect question. What is this for if we are just moving one amino group from one acid to another? Okay, it doesn't really help, does it? Well, it can help because, for example, we need a different amino acid, so we just take an oxo acid and make it into an amino acid. Okay, so we can synthesize an amino acid that we're missing by using an oxo acid and adding an amino group to it. So that's one thing. But actually, transamination is super important also for the degradation of amino acids. So if we want to break down an amino acid, we usually start with transamination, with removing the amino group, okay? But then, of course, we make another amino acid. Okay, so it doesn't help in any way. For that, we have another reaction. Okay, because most transaminations in degradation of amino acids is something that we'll cover in, a few weeks' time. But in most transaminations, the acceptor, the oxo acid which is used, is always the same. Okay, it's not always the same, but in majority of reactions that we'll see, it is the same acceptor of the amino group, and it's ketoglutarate. It's 2-oxoglutarate. Okay, I will add it here, but that doesn't mean that it has to be, okay? But 2-oxoglutarate is the acceptor, which means that it forms which amino acid? Does anyone know? This is an oxo acid, 2-oxoglutarate, and if we add an amino group, close, but glutamate. Yeah, we would form glutamate from it. Which means that basically as we break down proteins, as we break down amino acids, we would accumulate more and more glutamate. Yeah? And we can't just transaminate glutamate because that would just mean moving the amino acid to something else. So we have to have a reaction to remove the amino group from glutamate. And there is a special reaction which is not a transamination reaction, it's a deamination reaction. So that's another reaction that we're coming to, which is called deamination. And it's really a reaction, just one second, it is a reaction of glutamate. There are deamination reactions for other amino acids as well, okay? But the usual one that we'll see is the one with glutamate, where we remove the amino group to make ammonia, so inorganic nitrogen, and we form an oxo acid, which in this case is, if we remove the amino group from glutamate and we make an oxo acid, it will be 2-ketoglutarate or 2-oxoglutarate or alpha-ketoglutarate, whatever. Yeah? So this is called deamination reaction. And it's not just deamination, because we also need to oxidize the molecule. So this reaction is actually called oxidative deamination. Of glutamate to 2-ketoglutarate. We'll only see deamination, as far as I know, we'll only see deamination for glutamate. It does exist for other amino acids, but we'll not really cover that in metabolism. I don't think so. Okay? So we'll really only see this oxidative deamination of glutamate to ketoglutarate, because that is the only way how this nitrogen, which is accumulating in glutamate, how to get it out of glutamate and do something else with it. Okay? Because this then gets turned to urea in the urea cycle. We'll cover that, so don't worry about it now, okay? This will, in the end, get turned into urea in quite a complicated metabolic pathway. But this oxidative deamination is a super important reaction, and the enzyme that catalyzes this reaction is called, and again, that's a little bit counterintuitive maybe, it's called glutamate dehydrogenase. No, they're not. There also exist deaminations which are not oxidative deaminations. I'm showing you one specific type of deamination, which in this case is called oxidative deamination, because there is deamination and then there's oxidation in order for the keto group to be there. So where is the misunderstanding?
Is that, like, for example, let's say this is the starting product, this is the final product. So what happens is that here, like, we removed the NH2,
yep,
and we technically added an oxygen, right?
Yes.
So in all cases of transamination...
No. No. In transamination, there is no redox reaction. We're not oxidizing or reducing anything. We take an oxo acid and an amino acid and we swap the two groups. No redox reaction going on. It's only in the deamination of glutamate where we are not swapping anything. We are removing directly the ammonia. Okay? But in order for this reaction to run, we also have to oxidize the thing. So we actually, another product that we get out of it is NADH. Or 2 electrons, I'll put it that way. 2 electrons are removed at the same time. Otherwise it wouldn't work. So this reaction is called oxidative deamination. And it's really connected to the transaminations because in the end we have to deaminate the glutamate. At this point, again, take it as a preparation. We'll cover, in metabolism of amino acids, we'll cover all these reactions again, okay? So this is just a connection of different mechanisms that you might find useful later on, but we'll cover it in detail later on as well.
Why especially glutamate?
Because that's how it works in our body. So most amino acids will be transaminated onto glutamate, and then from glutamate we just scissor off, we cut off the amino group to give ammonia, and then in the liver it's turned into urea. That's how it's set up. Okay? Yes?
So glutamate actually is the donor of amine group?
It can be. So if we want to make, for example, alanine, yeah, we would take pyruvate and glutamate and transaminate them, and we would get alanine and 2-ketoglutarate. So that's a common reaction that occurs in our body.
Only glutamate can do it, or another?
Usually it is glutamate. It is possible to use other ones, but in most transamination reactions, one of the partners is ketoglutarate or glutamate. It's a very common thing to see. Good. There are other transamination reactions, but often it is 2-ketoglutarate to glutamate. Yes? Yeah, glutamate dehydrogenase is an enzyme which catalyzes oxidative deamination of glutamate. And it's called dehydrogenase because there's this oxidation bit as well. So it should be called glutamate deaminase, okay, maybe. But since it is a special type of deamination, it's oxidative deamination, it's called glutamate dehydrogenase. Okay. All right. Moving on, we'll have a look at, basically one more reaction in more detail and then 3 reactions in much less detail. I'll just tell you what goes on, so we'll manage probably quite easily. So the next pair of reactions is esterification and hydrolysis of esters, or deesterification. So esterification is a special type of a more general class of reactions called condensation reactions. A condensation reaction is a reaction where 2 molecules are joined together and water is released. That's condensation. Okay? 2 molecules join together and water is released in the process. So, for example, when we saw the reaction of pyridoxal phosphate and amino acid, this was a condensation. The formation of Schiff base is a type of condensation. Water is released and 2 molecules are joined together. Okay? Esterification is another type of condensation. 2 molecules joined together, water is released. What are the 2 molecules which are joined together in esterification? Alcohol and an acid. It doesn't have to be carboxylic acid, and we'll actually see very soon different types of esters which are not with carboxylic acid, but it's an alcohol with an acid. That's what we'll see generally, okay? Now, first type of esters that we'll see quite commonly, well, actually, generally speaking, esterification requires the addition of some work. We have to do some work. It's not a spontaneous process, okay? So we have to help it. On the other hand, hydrolysis, which is the opposite, generally does not require energy, okay? So esterification is something, or condensation is something where we need some help, okay? The hydrolysis usually proceeds spontaneously. A common type of esters that we'll see are esters with phosphoric acid, called phosphates. Okay, so the esters are called phosphates. If a molecule carries two phosphate groups, which are bound as esters, it's going to be called bisphosphate. So for example, when we have a glucose molecule that contains two individually bound phosphate groups, it will be called glucose, whatever, 1,6-bisphosphate. On the other hand, we just saw some coenzymes which were called diphosphate, like thiamine diphosphate. What is a diphosphate? Well, yeah, but now we just said that it's called bisphosphate when there are two phosphates in a molecule.
Maybe connected to each other
You're getting closer, but it's not an ester bond.
because that's maybe connected to each other.
Yes. A diphosphate means, so a phosphate looks like this. Okay, that's a phosphate. A bisphosphate will look like this. That's a bisphosphate. And a diphosphate is an anhydride. Correct. So this is an ester bond. 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 But this is an anhydride bond.
Are there carbons in this?
Well, here are some carbons, for example. Okay, we don't care about carbons now.
Because they're necessary for it to be this phosphate.
Well, yes. I mean, yeah. Of course, there are some other atoms here. Yeah, absolutely. Yeah.
Because of the diphosphate.
Of course, here the two phosphates are directly connected by an anhydride bond. Okay? So the two things are quite different, and they also have different nomenclature.
Wait, does the upper phosphate have, what's the deal with the oxygen in between?
Here is one which is connected to this one, and here is the other one which is connected to this one. They have nothing in common. Okay? So bisphosphate, trisphosphate means individual ester bonds. Diphosphate, triphosphate means that the phosphates are connected by anhydride bonds. Okay?
Can the distance between the two phosphates and the bisphosphate be known as a what's few or less?
Yeah, whatever. They can be in other parts of the molecule. Yeah. It just means that you have more than one phosphate in the molecule. Good. This is important. We'll use this nomenclature. Okay? So that is one type. Yep.
Why did you just add the carbon?
Sorry?
You just added the other carbons, right?
Yeah, because it's some molecule. Who cares? Okay? It's some molecule that has two carbons and there are two phosphates bound to them. The enzymes that catalyze the addition of phosphate groups are called phosphorylases. And if the phosphate groups come from ATP, then they are called kinases. So we have phosphorylases and kinases which catalyze the formation of phosphoric acid esters, okay? And they differ in where the source phosphate comes from, basically, okay? The enzymes that remove phosphate groups, so they hydrolyze these esters, are called phosphatases. Sorry, phosphatases. Phosphatases. Okay, so we have phosphorylases and kinases, and on the other side we have phosphatases which remove the esters. We will see other types of esters in metabolism. For example, esters between alcohols and carboxylic acids, which are commonly found, for example, in fat, in triacylglycerols. Okay, those are esters between fatty acids and glycerol. So those types of esters we'll see, but we'll also see a few times in metabolism a very special type of esters. And those are esters between a carboxylic acid and coenzyme A. Now, coenzyme A, another coenzyme, very useful for moving fatty acids around or acyls around. We'll see it many, many, many times in metabolism. Coenzyme A, I'm not going to show you the whole structure, but coenzyme A ends, one end of the molecule, it ends with a thiol. So it's like an alcohol, but it's an alcohol containing sulfur. So it's called thiol. Okay, this CoA stands for the whole big molecule that I'm not going to draw. Okay. Now, if we react this thiol of coenzyme A with a carboxylic acid, we get a thioester. So, for example, we could react it with acetic acid. Okay, that's not how it works, but I'm just going to show you schematically. Okay, and we can make a thioester with coenzyme A, which in this case will be called acetyl coenzyme A. But interestingly, it's not a normal ester, it's a thioester, which is a very different set of properties. Yep.
Is the thiol considered part of the coenzyme?
Absolutely. It's the end of the molecule, okay? So I'll show it, like, imagine that this CoA was a very complicated molecule, and at the end is a thiol. It's always the case.
The thiol is the thing that coenzyme.
Absolutely. So the same way as pyridoxal phosphate is an aldehyde group, which is important, coenzyme A is a thiol group, which is important.
Like, this is like, can we generalize that thiol is like the reactive part of the coenzyme?
Yeah, it's the part to which we bind things. Okay, the other parts are there just for manipulation. Yeah, okay, so this is the hook of the coenzyme. So these thioesters will come across quite often, and similar to some of the other esters, we need some work to do in order to make the thiol group, the thioester group, or the thioester condensation. But once we have put the work in, these thioesters can be considered activated, sort of, okay? We'll talk about what that means. And it's very easy to take this acyl and move it to some other molecule. So we do work, we put in work to make the thioester, and then we don't have to add any more work because it's hidden in the molecule already, and we can use it then to do some reactions which normally would not occur, okay? So this is sometimes called activated acyl. That's what they call this thioester between a carboxylic acid and coenzyme U, activated acyl, because it's activated in a way that we don't have to do any more work to have it react with things which normally a carboxylic acid would not work with. Right. Very special type of esters. We'll see them quite a few times. Right. Next reaction is going to be relatively quick. Next reaction is the formation of an amide and the removal of an amido group. Okay? So the formation of an amide, I think we'll only see in one reaction, which is the synthesis of glutamine. So if this is the side chain of glutamate, okay, this is the side chain of glutamate, in order to synthesize glutamine, we add ammonia and we make an amide, in this case, glutamine. For that, we need ATP. So it's not a spontaneous process. We have to do some work to connect these two molecules together. And it is the formation of an amide. It's an amidation. Okay? So it's a formation of an amide. We can also do the reverse reaction, so hydrolyze the amide, so from glutamine to make glutamate. And for that, we don't need to do any work. We don't have to add any ATP. We just hydrolyze the amide without any need for anything. Okay? So the reverse reaction occurs by a different reaction mechanism, and we don't have to add anything at all. It just removes the ammonia. Okay? So it's not the same enzyme, it's catalyzed by a different enzyme. This one is called glutamine synthetase, and this one is called glutaminase. Different enzymes doing different things. Okay? But one adds an amido group, and the other one removes an amido group.
Can you please repeat the names?
So this one is called glutamine synthetase. Glutamine synthetase. And the other one is called glutaminase. Once again, enzymes that we'll see again when we talk about the metabolism of amino acids, and we'll see them again when we talk about metabolism of the nervous tissue of the brain, because they're quite important in there. Okay? So this is, again, preparation, and we'll cover them again in more detail once we get there. Couple of final remarks, I would say. We will see another type of condensation, which is, okay, I won't tell you about this other type of condensation. We'll talk about it next week, okay? I won't tell you about that. It's a little bit too complicated, I think, for now. So let's leave that aside. So the final set of reactions that I just want you to know about, because they have important coenzymes that go with it. And those are transfers of single carbon fragments, basically of methyl groups. Okay? So we have enzymes that take a methyl group from somewhere and put it onto something else. Okay? They're called methyl transferases. And they are useful in many reactions. Again, we'll see them in a few metabolic pathways, these methyl transferases. So this is a methyl. I put it in square brackets because it's not a free thing. Okay, the methyl is always bound to something. And these methyl transferases have quite typical coenzymes which are connected to their function. One such typical coenzyme with methyl transferases is vitamin B12 or cobalamin. Cobalamin B12, okay, is a typical coenzyme of methyl transferases. Actually, vitamin B12 or cobalamin is present only in 2 enzymes in humans, but very important enzymes. We'll learn about them later on. The other important coenzyme for methyl transferases is called tetrahydrofolate. which is derived from folic acid as a vitamin. Tetrahydrofolate. Cobalamin is a coenzyme derived from vitamin B12. And it's a coenzyme of methyl transferases. One of them is a bit of a weird transferase, but anyway, yeah. So these are two coenzymes that we'll see quite often in relation to methyl transferases, and I will mention another coenzyme which is really a co-substrate of methyl transferases, which is called S-adenosylmethionine. S-adenosylmethionine, adenosylmethionine. And the interesting thing about S-adenosylmethionine is that it contains a positively charged sulfur. It has a structure like this, where there's a trivalent sulfur which carries a positive charge. So we saw today a negatively charged carbon, very unusual. Here we see a positively charged sulfur, interesting. And it's a donor of methyl group. Again, something that you will see again once we get to the specific reactions. Which enzyme? They are generally called methyl transferases, okay? But some of the specific types of these enzymes that transfer methyl groups have different names. But you could say they are methyl transferases. Okay. Not always, but generally they're called methyl transferases. Last few things before we finish, because there are a few trace elements that I just want to mention because we haven't covered them yet, okay? So which elements did we cover as cofactors of enzymes? Iron, copper, and zinc. Yeah? Those are the three that we covered already. Here is another one. Part of cobalamin is cobalt. So that's the only place where cobalt is used as it's not really, it's part of the vitamin, but it's really an ion of a strange metal, which is used in metabolism as part of cobalamin, so that covers cobalt. We also use in some enzymes, we use manganese. And one typical enzyme that we'll see again, which uses manganese, is an enzyme called superoxide dismutase, which is a very important antioxidant enzyme in our mitochondria, but also outside of mitochondria. So manganese is used in a few enzymes. One of them is the superoxide dismutase. We'll hear about it again. We also have in our enzymes, 30 seconds, okay? We also have in our enzymes molybdenum. So molybdenum is present in one or two enzymes in metabolism, and we will see it in one of the enzymes that is used in degradation of nucleic acids, which contains molybdenum. It's called xanthine oxidase. We'll see it again. And the final metal ion that I want you to know about is magnesium. And magnesium is used widely, practically everywhere, where ATP is consumed or synthesized. Because magnesium, as we saw the structure of a diphosphate, well, I'll do it the other way around. Sorry. So in a diphosphate or a triphosphate, there are a lot of negative charges on these oxygens. And it's very difficult for the enzymes to get in and do something, or for water to get in and hydrolyze it. And that's why we need magnesium, which binds to these negative charges and stabilizes them and allows ATP to hydrolyze. So whenever ATP is synthesized or hydrolyzed, magnesium is going to be there. It's going to be required for the function of the enzyme. That's it. Questions? Really? Yeah, there's a question?
Just like
Could you just be a little quieter? Yeah.
After what you said about covering afterwards, I just
Okay, we can sort that afterwards. What I think would be useful to take from these 2 lectures, apart from all the stuff that we covered, is that we will be using chemical structures to illustrate what goes on in the metabolic pathways. So if at this point you're not entirely comfortable with seeing these structures and understanding what they denote, please, please, please use the workbook for the first course and potentially for the second course to get familiar with these structures, because we'll be using them in every metabolic pathway. We'll be drawing these structures. I'll be just saying, okay, so here's a hydroxyl which will get oxidized to an oxo group. And it's really important for you to be comfortable with this. So use the time before we get into the actual metabolic pathway, which starts next week, okay? Use the time to really familiarize yourselves with the nomenclature, with what kind of functional groups you may come across, etc. Okay? It will be very, very useful if you do that. Yeah, of course. Yeah. As deep as possible. No, not enzymes, but the metabolites you should be able to draw, yeah.